Hi everyone, am I audible to you guys? Can anyone reply if I'm audible?
Yes, ma'am.
Good evening, everyone. I'm Shefali Gabal, and I am a research scholar at IIT Madras. And this is our second TA session on the topic basic construction material. So first, we will just see what we you might have studied in the week two of this course. So in this week two, you might have studied about the various different mechanical properties. So in last lecture, if you have remember, we have started the stress strain curve of different metals and how material stress strain curve differ. So what are the other different mechanical properties of our materials which we need to learn about for the designing of our materials? And then comes the non-mechanical properties. So, what are the different non-mechanical properties which you need to know before designing or before constructing any structure? And last thing is the what are the different design concepts of any material. So, if we go through the overview of this week, first thing is the mechanical properties of our material. So, first property is the viscoelasticity. So, what is the viscous? What do you call as a viscous material? Viscosity or so viscosity is basically resistance to flow. So if you see the first diagram, if a material is elastic, completely elastic material, then a stress strain curve, the phase difference between our two curves will be always zero. However, when we have a viscous material or we have a high viscosity, then the phase angle between the two curves will mostly be 90 degrees. So viscoelasticity is the property of the material where we have the both viscous as well as elastic property in our material. So if we see here our phase angle is almost between 0 to 90 degrees. So this is what we call as viscoelastic behavior of our material. Second thing is rheology. So, what exactly is rheology? When we are studying the science of flow and deformation in any material, that is called as the rheology. So, here you can see in various different material the resistance to flow the flow properties of our water is very flowable, oil is less flowable than water, then come the honey which is more less flowable than oil and water. So if we see in the civil engineering example, we have a tar coal. So this is the example of that tar. So the time which it take for one drop to go from here till this measuring class, that property when it is measured, it is called as the rheology of that material. Okay, so it is a actually a time dependent property of any material. The next thing is if we see what are the different type of fluids. So basically we have divided our fluids in Newtonian and non-Newtonian fluids. So material which are linearly viscous, like with increase in shear rate, the shear stress increases. This type of they are called Newtonian fluids, or the normal fluids which we see in the day-to-day life are called as Newtonian fluids. So these type of fluids are mostly incompressible, and the strain, sorry, the strain is non-recoverable in this case. Next come the non-Newtonian fluids. So all other type of fluids which are not Newtonian are called as non-Newtonian fluids. So in that also we have divided a non-Newtonian fluid at two parts, either shear thickening or shear thinning. So sorry. If the curve varies in this direction, if the curve is like that, then we are telling it is as a shear thickening. So this is the example of shear thickening. Mostly, if you might have visited any beach or something, this wet sand, mostly the wet sand, it will be it will be compressible. And when you will move away from that place, it will come back to its original place. So that is the example of shear thickening. Second example is shear thinning. So shear thinning example is like the self-compacting concrete. So self-compacting concrete, in that type of concrete, we do not require any vibrator or anything for the concrete to fill the gaps in between the rebars. So these are the different type of shear thinning and shear thickening non-Newtonian fluids. Other than this, we have other fluids like Bingham fluid, Harsher-Buckley fluid. Examples are given here. So our concrete usually come in the Bingham fluid. So it is almost like a Newtonian fluid, but it have a particular initial shear stress after which it starts showing the Newtonian behavior. So that is a concrete. So if we go to the next thing is the permanent deformations in the various materials. So, if we see due to the short-term loads, like mainly on the roads, if because of multiple loading or because of the settlement of the soil underneath the road, there is a rutting problem in our roads. Other thing is because of too much heat, sometime our bitumen will start compressing. So that is also one type of permanent deformation due to short-term loading. Next thing is permanent deformation due to the long-term load. So permanent deformation due to the continuous long-term load, that is what we call as the creep behavior of our system. So if you see in this concrete bridge, there is a small deformation here. So this is because of continuous loading or continuous moving of vehicles along this road. And second, other example is in the wood. So you might have seen the sleepers of our any railway track. So if these sleepers nowadays, these sleepers are made of mostly concrete. So if we have a wooden sleepers, normal it will be in the straight thing. So due to the continuous loading of our rails, there will be a permanent deformation here over the time. So that is called as the creep in the wood. Next thing is creep in our metals. So if you see this is this is a metallic pipe going around. So due to the loading of our water, since continuous water will be filled there, and it is hanged only at the 2 points. So there is a creep or there is a deformation at this point. That is called as the creep in the metallic pipe. So next thing is if we will see this creep and relaxation behavior from a graph. Sorry. So this wire, if you see, it will might be straight, right? Because of the this loading of our hangers, in this case, hangers, it will deform at this point, right? So after you will remove this clothes, it will again go back to the straight line. But over the continuous period, like after few months or something, you will see a permanent deformation in this wire of yours. So that is called as the creep behavior. So if we say strain versus time diagram of our any material, this period where strain is completely increasing due to the continuous loading is called as the creep behavior, and after the load is completely removed, that time there is a period which is called as the recovery period. Okay. Next thing is relaxation. So in relaxation, if you see the strain versus time diagram, relaxation will be like continuous straight line. So this is the strain versus time. And in if we see the stress versus time behavior, so in creep, when there is a continuous loading, that time stress will be high, and when the load is removed, stress is suddenly reduced to zero. However, in our relaxation behavior, stress versus time is the like a what we say parabolic or almost linear behavior, linearly reducing. Stress will be linearly reducing in case of our relaxation behavior. Okay, so this is what we'll say different type of permanent deformation in our materials. Next thing is what are the different viscoelastic material models. So if we say if we see any spring kind of thing, if we have a spring, that time what we are doing, if we draw force versus F versus T diagram, so what will happen if we are at particular time we are increasing strain, then we are continuing it, and when we release it, again our spring will go back to the original position, right? So our behavior will look like this in our spring model, right? Next thing is our if we first we will go to the dashboard model. In our dashboard model, there is a attachment, and then we have a dashboard and load is applied. In that case, what is happening? If we see any deformation versus time graph. Okay, first we will see force versus time graph. Force versus time graph will be similar to as compared to the spring, right? Force is initially suddenly forces increase, then continuous force is there, and then suddenly force when force is removed, it will reduce to zero. So in deformation versus time graph, what is happening? Uh, Deformation, there is a sudden deformation, like continuous deformation, and when the force is removed completely, we have a permanent deformation. So that is a dashboard type of model. Next thing is Kelvin model. So in Kelvin model, what we have is we have a say deformation versus time graph. So in Kelvin type of model, what we are saying there is a it will have a behavior similar combination of both spring and dashboard. So initially it will be increasing linearly, increase suddenly. Then there is a linear increase, and after linear increase, when stress is removed, there is a decrease, and but it won't go back to the original position. There will be a what we'll say recovery period, like in the creep graph if you have seen. So it will have a similar kind of behavior. Okay. So what other thing you might have studied in this week is the ductile to be sorry ductile to brittle transition. So before going to ductile to brittle transition, first we will see what are the different brittle and ductile failure. So how will say if a material is breaking suddenly, we are telling it is a brittle behavior, and if it will deform and then fail, it is a ductile behavior. So if you see in this diagram, this is a for the metals, ductile and brittle behavior. So if any metal rod is stretched, a tensile force is applied to it. Normally, what will happen? A necking will be forming, and then there will be a deformation, right? However, if there is a sudden deformation, if it suddenly breaks, then it will show this kind of shape. So this is a brittle behavior and this is a ductile behavior. So normally our mild steel will have ductile or brittle behavior. Any idea? Normally our mild steel will have a ductile material behavior. That's why we are using it as a reinforcement. So if you see our concrete, normal concrete, if in a normal concrete beam we are applying a tensile force in this and that way, so what will happen when force is applied? It will fail suddenly. So we usually say our concrete is weak in tensile failure, right? That's why we are providing rebars into it. So if we see this concrete will have a rebars inside it. Rebars are put in tensile strength. So what will happen? The failure won't be the brittle failure. It will first crack will initiate, different crack will be there, and then that cracks will be propagating. So that will be a ductile failure. So if you see from the stress strain curve, in a ductile behavior, the area under the curve will be very high, whereas in the brittle behavior, the area under the curve will be very low. Okay, so these are the various ductile and brittle failures. So next thing is what will be the ductile to brittle transition. So normally the materials like metal or something, they are initially in the ductile uh, they are they have a ductility, good ductility. However, because of the temperature change, there can be a chances that the ductile material is changing it to brittle material. So if we see this example, our mild steel at higher temperature, mild steel will be showing a ductile behavior. Okay, if the temperature is reduced to minus 150 degrees, suddenly the impact energy absorbed will be small. So if we see the lesser the energy absorbed, more is the brittle behavior. So if we see a mild steel, when the temperature is reduced to minus 150 or minus 100 degrees Celsius, our materials start behaving as a brittle material. So this is the one of the example of the ships which suddenly failed, and when they check the cause of the failure of this ship, it was shown that because of the very low temperature in the water or in the area, there will be a sudden there was ductile to brittle transition and the ship failed. So the temperature at which the slope of this curve, so if this is the slope, uh, imagine at this point, this is the slope. So any point, any temperature at which this slope have the maximum value, that will be called as a ductile to brittle transition temperature. Okay. So next thing what you might have studied in this week is what is the different area under the curve of our stress rate curve, what it is called as. So if we see this enormous stress strain area under the it will go elastic and then strain hardening that kind of. So within the elastic area, this area under the curve is called as modulus of resilience. However, when we see the complete stress strain curve, the area under the curve is called as the toughness, and the point at which the material fail is called as the fracture behavior. So if we have to compare two type of materials which have a very high this slope area, very high slope area that will have a high toughness. However, the material which have a very high stress value, ultimate stress value will have a high strength. Okay. So next thing is fatigue failure. So what is fatigue failure? Because of continuous loading when our material fail. Just a minute. So, due to the fluctuating loads, continuous fluctuating loads, when a material fails, that is called as the fatigue failure. So, this is an example. This is one mild steel or any metal. Initially, a small fracture will be there, then it will start propagating, and at one point, when this fracture have went inside a lot, then suddenly there will be a sudden failure. That is the catastrophic rupture of our material. So that is a fatigue failure. So if we go to fatigue failure thing, we can see that there are three main points. First is the we have a crack initiation. Crack will initiate. After that, crack will propagate, and then there will be a final failure or catastrophic failure of our material. So sorry. If we see different, next thing is how we are understanding this fatigue failure. We have the SN curve. So what is SN curve? It is the stress versus cycle failure. So different cycles, cycle of load will be applied. It will be unloaded, loaded, unloaded, loaded, unloaded. That is called as the cycles. So different based on different cycle versus stress, we are having SN curve. So point at if we say number of cycle for a material, number of cycle required for a material to fail is called as the fatigue life of our material. And next thing is fatigue limit. So what is the fatigue limit? A stress below which fatigue failure will not occur. So that is called as the fatigue limit. And third thing is fatigue strength. So fatigue strength is the stress at which failure will occur at a specific number of cycles. So that are the three type of things which we need to get from the SNN curve. Next thing is the what are the different. So this is all different type of mechanical properties of the material which you will be requiring to design a new material or understand a new material if you are bringing a new material into the construction industry. Other things are the non-mechanical properties. So mainly non-mechanical properties will be affected by the five senses of human body, and if we distribute it, it will be acoustic. So sound insulation and how our sorry sound control, sound absorption, noise barriers, and then if we say smell, then smell of paints, woods, different type of material which you are using, it should not smell bad. Next thing is aesthetic. So it should look aesthetically any structure, whether it's home, bridge, or any building, it should be aesthetically uh, good or beautiful, we say. So Along with the seeing the structure property, we should also see that its aesthetics are good, it have good ventilations and all those type of property. And last is the thermal comfort. So it should not be like your home or any room doesn't have windows or have proper ventilation, have proper thermal comfort. It should not be too hot, should not be too cold. So these are the different non-mechanical properties which you need to understand before designing any structure. Last thing is the what are the design concepts which we need to keep in mind. That is a 4S design: strength, serviceability, service life, or what we say durability, and sustainability. So based on these 4S design, we'll be going ahead and doing our design. So this is all an overview of what you might have studied in this week too. Anybody have any doubt, you can ask me now. Otherwise, we will go to the question and answer session for today. So, if you guys have no question, then I'm assuming that whatever have been taught in week two is clear to everyone. So, we will see the different questions. So, the first question is a steel bar of constant circular cross section has the initial diameter of 1 centimeter. When it is subjected to a tensile force of 50 Newton on both ends, the area is reduced to 70 mm square. Calculate the true stress and engineering stress at this moment. So you can try once. So if we say stress is equal to force upon or load upon area. So what is true stress and engineering stress? Just try to calculate it. Okay, first we will try to understand what is the difference between the true stress and engineering stress. So normally when we are telling engineering stress, so in engineering stress we will take the initial parameters of our material. Or in this case, if we are having a circular road, so we are telling the initial cross section of a circular road will be giving us the engineering stress. However, true stress is the stress at the point of deformation or at the point of calculation. So if we say stress is force upon area, if we have to calculate engineering stress, then force will be constant. Force is 50 Newton and area will be what it is given, cross sectional of initial diameter of 1 centimeter. So it is a circular, so area will be pi by 4 d square. D is 1 centimeter, which is equal to 10 mm. So if we will calculate it, it will come as 50 divided by pi by 4 into d square. I will calculate it. It is coming as 78.5 0.53. So calculate this thing. What value you are getting? So it is approximately 0.636. Okay, that will be our engineering stress. Next thing is true stress. So in true stress, what is this given that when it is subjected to tensile force, the area is reduced to 70 mm square. So our initial area was 78.53 and the area is reduced to 70 mm. So directly if we calculate 50 divided by 70, what we are getting? It is 0.714. So our answer will be true stresses 0.714 and engineering stress 0.636. Okay, is that question clear? Okay, we'll go to the second question then. Unstable necking occurs before strain hardening in hot rolled steel. Straight to true or false? Any guesses? What do you think? It will be a true statement or false? So if we check the answer, it is a false statement because in case of hot rolled steel, the necking will be proper and it won't be before strain hardening. It will be during strain hardening. Okay. So next question is the impact energy absorbed by the sample dash as the failure mode of the material changes from ductile to brittle. Increases, remains the same, decreases till the ductile to brittle transition temperature and then increases. So if you remember, this is the energy absorbed, the area under the curve. Impact energy absorbed by the sample as the failure mode of material changes from ductile to brittle. So what will happen? It will, this curve is for ductile material and this is curve is for brittle material. So if our material is changing from ductile to brittle, this absorbed energy will be decreasing. Okay, here. So next question is, during the creep deformation of steel, A is constant, whereas during the relaxation of one point steel, during the relaxation of steel, B is constant. What are A and B? A is the stress acting and B is the strain. A is the strain and B is the Poisson ratio. A is the Poisson ratio and B is the stress acting. What is the previous answer? Okay, this one. Question number 3 you are asking
Yes, ma'am.
is decreasing. So if you can see from this graph, from ductile to brittle, if you are going, the area under the curve decreases. So energy absorbed is decreasing. Okay. So if you remember, we have seen the graph of creep and relaxation. Creep was like this.
It's constant as reduction is 1.1.
Can you mute yourself? So these four curves was there. This was for creep, and these two were relaxation. So this one is the So what is being asked here? What is that value which is constant in case of creep, and what is the value which is constant in case of relaxation? So in this case, if you see, we have to find the constant value. So we have to go around with these two graphs. So you remember what were these two graph about? So x-axis was always time in all cases. So in case of creep, this was stress versus time, and this was strain versus time. And in case of what is say? In case of relaxation, this was stress versus time, and this was strain versus time. So if we see the option, in case of creep, stress is constant, and in case of relaxation, strain is constant. Okay. Okay. So we'll go to the next question. Figure 3 shows the variation of shear stress to shear strain rate for different materials A, B, C, and D. So consider the rheological properties and assign appropriate material for A, B, C, and D. So, okay, you can take some time. These are the different, shear stress versus shear rate curves. So, if you remember, we have talked about D will be Newtonian fluid, all three will be non-Newtonian. So, based on the different example, what do you think? Which of the following do you think will be the Newtonian fluid? Option are toothpaste, tomato ketchup, cornstarch, or water. So normally, what we was telling that normal fluid or what we say water will be a Newtonian fluid. So D will be 4. Okay, Newtonian fluid is water. Then come the non-Newtonian fluid. So first we will see the B. B part was shear thickening. Shear thickening means what example we have seen before? We have seen the before the example of uh, mud at the beach part, right? So what do you think can be a shear thickening material? Toothpaste, cornstarch, or tomato ketchup? So normally if we see what will be the thicker material? To tomato ketchup. Tomato ketchup will have a shear thickening type of consistency. And then no, sorry, this is shear thinning. Tomato ketchup will have a shear thinning kind of material. And then we have shear thickening. So shear thickening is that mud one only. So when you are pressing it, it will be harder. When you are releasing it, it will be like a fluid. So that will be like a cornstarch in water. So you can try this experiment. You can add cornstarch in water. When you will press it, it will be like a thick, solid thing. And when you will release it, it will be like a fluid. So that is a shear thickening material, B part, that will be cornstarch. And last is the A. A will be the Bingham fluid that we were telling about our concrete. Our concrete is a Bingham fluid. So in this case, toothpaste is actually similar to the Bingham fluid. So the option is A1, A, A1, B3, C2, and D4. So C will be the correct answer. Okay. Okay, we'll go to the next question then. Using the concept of energy absorption capacity, which of the following would be good choices of material for designing a slab on grid exposed to cyclic variation of ambient temperature and soil with swelling characteristic? So two options are correct. So if we want a uh, cyclic variation of ambient temperature, that means we can't use the uh, we, what we have to design. We have to design our road top surface slab on it, and at that point we have an ambient temperature. Ambient temperature means normal temperature, and the soil, but the soil have a swelling characteristic. In that kind of case, we can't use the plain cement concrete, right? Because cement will have cracks. Second is asphalt concrete. So since we have ambient temperature, temperature is not rising too much. That means we can use the plain asphalt concrete. Third is fiber reinforced concrete. So fiber reinforced concrete will be very good in case of both the temperature and the soil beneath having a high swelling characteristic. Last is lightweight aggregate concrete. So if we are having lightweight aggregate concrete, what will happen? Because of swelling, it will be easy for our on subgrade to break, or sorry, not subgrade, slab on grade to break. So the correct option will be B and C. Okay. Okay, then we will see the next question. A building in Chennai is required to be designed for good comfort. Among the options given, which of the following type of wall plaster system is the most efficient system? Choose only one choice. The thickness of all the walls are same and all the plasters are same. So we have to design a building in Chennai which have a good thermal comfort. So what do you think? Should we use brick wall and cement plaster, concrete block with the dense plaster, lightweight concrete block and the lightweight plaster, brick wall and the thicker cement plaster? So in Chennai, we have a very high humidity and we don't have too much cold. We have a very normal temperature. So in that case, what do you think would be a good combination? So in area like Chennai, where you have a high humidity and normal ambient temperature, it is you cannot go for the denser concrete blocks because it will be too hot. And then you cannot go for the brick wall also because you need good thermal comfort and brick wall will absorb heat. So the last option is lightweight concrete block and the lightweight plaster. Okay. Okay. So what is an SNN curve? How to use it and what property of material does it show? So why we are using SNN curve? We are using SNN curve in case of our fatigue failure, right? So SNN curve is S means stress amplitude versus cycle of failure. Anybody who want to say few words or want to add up something about SNN curve? We have already discussed about it. So if we see and these are the two SNN curve. So any point where we have the when failure occurs, the cycle at which a number of cycle at which a failure occur is called as a fatigue life. So in this case, what will be a fatigue life? Any material you can take. So point at which this curve will get straight, that point will be our uh, fatigue life, the cycle at which this curve will become straight. That point we have a failure that is called as a fatigue life. Next thing is this point at which this curve is, if our curve is getting like this point is called as our endurance limit. So maximum stress it can take before failure, it is called as our endurance limit, and this point maximum cycles at which it is failing is called as a fatigue life. If material A is failure mode, material B is failure, have a less failure. Okay. Material A have a more failure as compared to material B, you are trying to say. Material A have a higher failure rate. Okay, so it will fail before material B, right? So it's if we say the point at which this material A almost will fail at this cycle and material B is almost failing at this cycle. However, it can endure more stress as compared to material B. It will fail before material B, within less number of cycle, material A will fail. However, material A can endure more stress as compared to material B at that point. So its endurance limit is more. However, its fatigue life is very less as compared to material B. So your answer is correct only. What other properties we can get from SNN curve? Fatigue strength. So fatigue strength is if imagine I told that my material have to endure 10 is to power 7 cycles of the uh, loading. So at this point, I will make a straight line and we will check the stress value at this point. So the stress value at a particular cycle, as a particular cycle of failure, is called as our fatigue strength. So which material have a higher fatigue strength? A will be having a higher fatigue strength at any point of time, right? So that is called as our fatigue strength. So if we have, so we can see our SNN curve in different ways. If we have to see how which material will endure more number of cycle before failure, then we will see B material is a good material. But if we have to design it according to the number of cycle, uh, which material can endure this much amount of cycles before failure, then we will check according to our fatigue strength. And if we see material A will be having a higher fatigue strength, even at the lower cycle, if we see before failure, material A will be having a higher fatigue strength as compared to material B. Okay, so these are the different kind of properties of material we can get from our SNN curve. So last question is, what is ductile to brittle transition of materials? So as we have already studied, ductile material will be having a higher area under the curve and brittle material will fail suddenly. Okay. So what is ductile to brittle transition? It is a temperature at which the slope of ductile to brittle sorry, ductile to brittle transition temperature is a point at which the slope is maximum. If the slope of our curve is maximum at this point, that is called as ductile to brittle transition temperature. And why ductile to brittle transition of material happens? It is normally due to the change in the temperature. So whenever a temperature suddenly decreases, normally it go beyond minus 50 minus beyond 0 degree Celsius, less than 0 degree Celsius at very low temperature. Normally our ductile materials start behaving as a brittle material, and there is a complete S type of curve which is called as ductile to brittle transition of our materials. And The point at which that slope is maximum is called as ductile to brittle transition temperature. So that is dB Pt. So that is called as ductile to brittle transition of materials. Okay, so that's all for week 2. If you guys have any doubt, you can ask me now, or you can contact me on my mail IDs also. So any questions? You can put in
Ma'am,
chat box. Yeah.
ma'am, can you please explain the very first question?
Can you please explain what?
The first question, hot rolled steel.
First question.
Yes.
Can you please type in the chat box? I'm not able to understand. Hot roast steel question. Yeah. This question only. So in case of our hot rolled steel, what is happening is if we see the stress strain curve, we are telling like this, right? This is a normal stress strain curve of our any metal. So in case of hot rolled steel, there will be a complete deformation of material from this point, and then this is the strain hardening area. So at this point, there will be a necking, and then there will be a complete ductile failure at the failure point, ultimate stress point. So here it is telling that in hot rolled steel, the unstable necking will occur before strain hardening. So it is a false statement because in case of hot roll steel, our necking will be like change from this type material from here to here. That breakage of our material will be completely stable. Why? Sorry, just because of the way this type of steel is being formed. So hot rolled steel is normally the type of steel which is uh, how we say it's normally being quenching and QST, normal QST steel will be our hot roll steel. So the type of necking or the type of failure in this type of steel will be proper and won't be an unstable type of. Whereas if we see the cold rolled steel is like it will be heated and then cooled suddenly. And that kind of steel, what will happen? There will be the ductility won't be much in the type of in our steel. The ductility will be very less and strength will be very high. So our strength value will be very high. However, our ductility will be very less. So strain hardening part will be decreasing in case of our cold roll steel. So in that case, this necking won't be there. There will be a sudden failure. Even not like sudden breakage. The necking will be there, but it won't be like a ductile failure. It will be little bit of brittle failure. So I hope this is clear with you. Any other doubt? Okay, if there are no doubts, then we will close the class for today. Thank you for joining.